Welcome everyone to tonight's talk on existentially closedness of Cuba as a globally valid field by Michal Szachniewicz. Oh, sorry. I should have.
It's Szachniewicz. Yes. Okay. So yes, thanks. I want to thank the organizer for letting me speak here and organizing this wonderful conference. And today I will talk about existential closeness of Cuba. So yes, so let's go. Okay.
No, this is the
No, this is not the PDF reader. This is the room by here. You can open the PDF reader so that.
Okay. Oh, it worked. Okay. So yeah. So we'll start with some motivation, and then get into some other topics. So let's just start. Okay. So I will recall on some things that Woody mentioned yesterday. So first of all, let me recall what height of a rational number is. If Q is A divided by B written in a coprime way, then height of Q is just logarithm of maximum of absolute value of A and B. So it's just a simple way of measuring the complexity of a rational number. Yes. And one can write it in a simpler way without referring to a presentation as a quotient of two coprime integers. So this is the formula, and the idea is that we can take different p-adic valuations in the sum weighted by logarithms of p. We only take it if it's bigger or equal 0, and then at the end we take maximum of minus logarithm of the absolute value of q and 0, and this is the same as logarithm of maximum of a and b. And this is because, well, you can see it on an example. If we look at 2 divided by 3, here 2-adic norm is positive, 3-adic norm is negative, but then 3 is bigger than 2. So at the end, at the complex place, we'll get logarithm 3 divided by 2 after all, so we'll get logarithm 3. Okay, and this is, I guess, like a warm-up. And in general, for an algebraic number in Q bar, we can define Weyl logarithmic height by the following formula. So here we normalize at the beginning by the degree of the extension of Q, where this small q belongs. And in fact, this doesn't depend on the number field that we take, where small q belongs. And here by kappa of p, I mean the residue field of the ideal p in the integer ring of the number field k. And in the rest of the talk, k will be a number field. Okay. So to write it in a more compact way, let's fix a measure on the space of valuations on the number field. So here in this talk by valuations, I will mean non-Archimedean valuations and Archimedean valuations. So for me, Archimedean valuation is minus logarithm of a norm coming from an embedding into complex numbers. Okay, so here I have this discrete measure that is set up so that it measures exactly height. And then we can write this height as an integral. So this will later resemble heights in GVF structures. Okay. So as Udi was talking yesterday, for a tuple in a projective space, we can define its height by using this measure by the following formula. So yeah, so this integral here, you can write it as a sum, but yeah, here it's written as an integral. And of course, if you have a point in a projective space, the projective coordinates are not unique, but this number is uniquely determined because of the product formula. So if we take different projective coordinates, then in the maximum, every term, we add valuation of q for some algebraic number q, but we have the product formula stated in this way here, which says that the integral vanishes. Okay, and so classically heights are useful in many considerations in number theory. So for example, in the proof of Mordell-Weil theorem, they play an essential role. So this states that an elliptic curve or an abelian variety, if one looks at number fields points, it's a finitely generated group. also in Falting's theorem, which says that whenever we have a curve of higher genus, then the set of points in any number field is finite. So it's very natural because they are just a basic measure of complexity of points. Okay, but in these cases, the degree is bounded, and in the case of Q bar, it's obviously not. So this will be a bit different flavored application, but okay. But I just wanted to say that heights can be useful. Okay, so yeah, so let's look at globally valued fields. Yes, okay. So first of all, from the point of view of measure theory, what is a globally valued field? So for me, a globally valued field is a field together with a measure on the space of valuations, such that it satisfies the product formula, and such that these functions evaluating valuation at some element of the field are integrable in this strong sense. Their absolute value is integrable. So a few remarks. So first of all, oh yeah. But yeah, so should we? Okay, let me just write it and I will be saying it. So hopefully one can recover it. So first of all, if it comes to valuations, one needs to consider real valuations. Otherwise, the product formula won't make sense. And so if you want to consider real valuations, you will be considering valuations. You may happen to consider valuation and, for example, 2 times valuation. So some measures are supposed to be identified. So this is why we look at class of measures, not measures themselves. So the point is that if V is a valuation, we can consider 2 measures. Dirac delta at V, and let's say 2 times Dirac delta of 1/2 V. And so they should be identified. But I don't want to get into the details of this equivalence relation that I'm dividing by the space of measures. And second of all, by valuations, I need, either non-Archimedean valuations or minus logarithms of absolute values of coming from embeddings into complex numbers. However, this definition only works for countable fields. So for uncountable fields, this space of valuations needs some care. But this isn't much of a problem, and I don't want to go into the details here. Okay, but one can see it also using predicates or unbounded continuous logic in the sense of Ite, for example. And to do this, one uses Q-tropical polynomials, which are just terms in the language of addition, minimum, maximum, and multiplying by rational numbers. And then if we have a tropical polynomial, for example, this presented here, then we introduce a continuous logic predicate, which takes, in this case, A and B, and associates to it an integral over the space of valuations of this predicate, of this tropical polynomial, where we apply valuations on A and B respectively. So we get this formula. Okay, and one can write universal axioms for these predicates. So obviously, for example, if one tropical polynomial is a sum of some other 2 tropical polynomials, then we'll get a sum axiom. It's the same with multiplication. The only axioms that require some care are positivity axioms, which will ensure that, for example, if t is maximum of x and 0, then this RT is non-negative. However, this can also be done in a first order way. So this is a more syntactic way of viewing GVFs. Okay. Okay, so let's talk about some examples. So also by height of an element here, I mean this integral, which in the Q-bar case coincides with the usual Weyl height. And first of all, by the formulas that we saw before, or by the measures that I defined in the motivation sections, we can see the algebraic closure of Q as a globally valued field, meaning that we either take this measure or the set of these continuous logic predicates that we looked at. And then, in fact, this GVF structure is unique up to multiplicative constant. So obviously, if you have a GVF measure satisfying the product formula, it's homogeneous, so you can multiply it by 2, and it still satisfies the product formula, and all the axioms are homogeneous as well. However, for Q-bar, it's a consequence of standard number theory theorems, so finiteness of class group and Dirichlet unit theorem, that in fact this GVF structure is unique. And so by Q of 1, we denote the GVF structure on Q with height of 2 equal logarithm of 2, and we can scale it, and then we write it Q of R. So this is one basic example. Second of all, in unbounded continuous logic, we can take ultra products, but then we only take sequences with bounded height. So this is another way of getting examples. And in the geometric case, whenever we have a base field K, we can equip the algebraic closure of K of T with a GVF structure. And there is a unique GVF structure on K of T bar that is concentrated with the measure concentrated on valuations vanishing on K, such that the height of T is equal to 1. So this is an analog of the first example in the function field case, where we have Riemann-Roch for curves, and we can use it instead of finiteness of class group and Dirichlet unit theorem to deduce this. And Itai and Udi have shown that this GVF structure is existentially closed. So yeah, in the context of continuous logic, you can think that being existentially closed, as usual, means that whenever you have a GVF extension, then the latter GVF can be embedded into an ultra power of the former, over the former GVF. Okay. And second of all, so this is what Udi was talking about yesterday. If X is a variety over K, we can fix a movable curve on X. So it's a curve such that there exists as a risky open subset where we can move the curve and cover this open subset, or we can fix codimension 1 many ample divisors, hypersurfaces coming from embeddings into Pn, and this induces a GVF structure on the function field. More precisely, if we fix the function field of the variety, then the set or the space of GVF structure on this function field, but then again concentrating on the measure with a measure concentrating on the space of valuations vanishing on K, is homeomorphic to the inverse limit of the cones of movable curves inside birational models of X. So this is a geometric description. But yeah, I won't get much into that because we will say a bit more about the arithmetic case. So yeah, so to give you some arithmetic example, I thought it would be nice to mention some arithmetic phenomena that is connected to GVFs in the arithmetic setup. So recall that Below equidistribution says that whenever you have a sequence of algebraic numbers such that the degree goes to infinity and the height goes to 0, then if we look at these discrete probability measures, so here we look at the Galois orbit of AN, and we put Dirac deltas at the orbit, and then we normalize so that the measure is probabilistic. Then Below equidistribution says that these measures weakly converge to Lebesgue measure on the unit circle. So obviously, if one takes the roots of unity, that's a prototypical sequence that satisfies the assumptions. And the roots of unity they equidistribute around the unit circle. That's quite clear. But the content of this theorem is that we only need height of an converging to 0, and then we get a behavior around the circle. Okay, yeah, maybe which one is it? Oh, this, okay. Yeah, so from the point of view of globally valued fields, one can see this as a consequence of the following fact. Namely, there is a unique GVF structure on one variable extension of Q bar, satisfying height of x equals to 0. So the sequence AN that we see in the below equidistribution, one can see it as converging to this unique type, satisfying height x equals 0. And more precisely, if one looks at the GVF measure, course that this extension induces on Q of x, then one can see the Lebesgue measure on the unit circle directly. So yeah, so for this, let me draw a picture. Okay, yeah, it should be enough. So okay, so in this case, what do we have? So we have measures on Q of x. So not measures, but valuations. So every valuation restricts either to the trivial one on Q or to some p-adic q-adic one, or restricts to just the Euclidean valuation on Q. So okay, so what are valuations on Q of x that are trivial on Q? So this is in bijection with P1 over Q or A1 over Q. Okay, here we get the Berkovich analytification of P1 over Q, or more precisely, Berkovich identification of this guy. Okay, and here we roughly get CP1, the complex analytification of P1 over C. So here we get the infinite point. Here we get, besides infinite point, we have complex numbers. On complex numbers, we have a unit circle, and on this unit circle, we can put the Lebesgue measure on it.
There is some identification.
Well, so for example, here, so for me, valuations in this case come from embeddings into complex numbers. So whenever you embed this into complex numbers, then Q goes to Q, and X can go to any.
Yeah, but for example, if X goes to I or minus I, you divide it the same.
Oh yeah, so yes, I should divide it by. Yes. There should be some identifications, but let me know. Yes. So here, points of P1Q. It is. Yes. Okay. So here we can put this Lebesgue measure on the unit circle. On the Berkovich space for each P, we can put Dirac delta at the Gauss point. And here, if we have a point corresponding to some corresponding to Q in Q bar, then we put weight height of Q. So this describes a measure on the space of valuations of Q of x, and this is the unique measure that extends the GVF structure on Q, the normalized one, and with height of x equals 0. So yeah, I thought it would be nice to give a concrete arithmetic example. But now let's go into existential closeness. So the main theorem of this talk is that if we look at Q bar with this normalized GVF structure, then in fact it's existentially closed. And let's look at this statement from the point of view of our predicates. Oh, thanks. So what does it say? Well, it says that whenever we have some equations, some affine variety, we can even assume that it's over Q, and we have some polynomials on this variety. Whenever we equip the function field of the variety with a GVF structure, and we look at some height equations, these RT are like height equations on the function field that is a finite extension of Q, then for any epsilon, we can, as generically as we want, solve them with a Q bar solution. So this is how always existential closeness looks like. We can go up, we have some equations. In this case, these are height equations, height conditions. And if there is a GVF structure that satisfies them, then we should be able to solve it already in Q bar with our standard GVF structure. Okay, so before getting to the proof, let me say something about applications. So first of all, a direct application, one can get out of it an L1 Fekete-Szego type result for varieties of arbitrary dimension. So I believe Udi was mentioning this yesterday. And so maybe let me say a few words about the standard Fekete-Szego. So if we have a compact shape in complex numbers, then one can associate to it an invariant called capacity. And then capacity is bigger or equal 1 if and only if for all open neighborhoods of C. There exists infinitely many Galois orbits of algebraic integers. So the integral closure of Z inside Q bar.
Bigger than 1, though. Less than 1, though. I'm not sure you can say what happens on Q.
I think for complex numbers, it's this one. In Rumley, there's this part where we don't know what happens when it's equal to 1. I think, but okay. Well.
No, I think the infinitely many go all the way to the break integer in any given open neighborhood.
Okay, so let me. So yeah, for any open neighborhood, for any open U, there exist infinitely many Galois orbits of algebraic integers inside U. Okay, and then capacity of C is smaller than 1, then opposite. Okay. Okay, yeah, maybe this is yes. Okay, so otherwise there exists an open neighborhood where we have only finitely many such orbits. Okay. Yeah, so this is Fekete-Szego. However, in GVF language, we cannot say that we are exactly algebraic integer, which means that all non-Archimedean valuations are bigger or equal 0 on this Q bar number, but we can give an L1 version of that. So we can say that the weight of all places where we're negative is smaller than any epsilon that we want. So that's why it's L1 Fekete-Szego. And second application is that the existential closeness allows to give a different alternative definition of the arithmetic essential function. So I will talk about that function later. there is also some potential application to Calabi-Yau type theorems. So the existential closedness in Udi and Itai's case, one can use it or its theorem to prove some Calabi-Yau type theorem over non-Archimedean fields. But non-Archimedean, where the non-Archimedean valuation comes from a point on a curve. But in this case, maybe one can use it over p-adic fields and yes. So this is a work in progress. And another thing is that in general, the prototypical example of application of these things should be that whenever we want to find some configuration of algebraic numbers satisfying some height conditions. So this is the case, for example, when one looks at heights on elliptic curves and one wants to look at how far height is from being multiplicative, like quadric like this, then instead of finding a sequence of explicit points, one can look for some measures, and it's often easier to look for measures than for points. Although, yeah, let's maybe get to the proof. So the proof uses oracle of geometry. So I thought I'd say a few words about oracle of geometry before outlining it. So the oracle of geometry here gives us a more conceptual understanding of these predicates coming from the definition of GVFs. So to say a bit more about it, let X be a smooth variety over rationals, and then a curly X is a Z model of X if it's a projective, normal, generically smooth, in our case, scheme over spec Z. Such that if we look at the equations modulo Q, we get X back. So for example, the projective space over Z is a Z model of the projective space over Q. However, we can do things outside of the generic fiber to still be a Z model of the Pn over Q. For example, one can take a point in some special fiber over the prime 2 and blow it up, do some geometric operations there, and this will still be a model of the same variety over Q. And the basic object of oracle of geometry that will be necessary for the proof is an arithmetic divisor. So an arithmetic divisor is a pair of a divisor together with a green function for this divisor. So a divisor, you can think of a linear combination of codimension 1 subvarieties. Although in the over spec Z, one should consider formally Cartier divisors. And a green function, it's a local parameter for analytification of D. So a function with domain like that is called the green function for D. If for any open subset of X, on which D is given by some local equation, if we look at the function G plus logarithm of the absolute value of this local equation, then this is in fact a continuous function on the complex analytification of this open subset. So maybe let me draw a picture of that. Here. Okay, so we have our arithmetic scheme. You can think that's a P1 over Z. We have some divisor, D. We have some open subset U, on which this D is given by vanishing of some function. And then we have a function G, but it's defined on the analytification of this part, where we have this property. So maybe, for example, if one looks at the divisor X equals 0 in A1 over Z, then a green function could be taken to be G is maximum of minus logarithm of absolute value of X and 0. So this function on the complex identification, which is just the complex numbers, looks like this. We have 0, which is the divisor. Over it, we have singularity. And then we take this maximum of this function and 0. So at some point everywhere here, we get 0. And if we add logarithm of absolute value of x to this function, then we get a continuous function on complex numbers. Okay, so also another example. If we have, should I? So if we have a rational function in the function field of our arithmetic scheme, it's the same as the function field of its generic fiber, so of the variety x over q, then we can look at the following divisor. So we take the zeros and poles of f, and we take minus logarithm of absolute value of f on the second variable. And now these adelic divisors have a structure of a lattice. So the point is that if we have two such divisors, sometimes it happens that their intersection is also a divisor. So this is very rare. This rather happens when they have a common component, but still it might happen. And in this case, we define the minimum of those as the intersection of the first variable and minimum on the second variable. But to force it so that we can always assume that the intersection is a divisor, we can pass to some other variety which has the same function field where this is indeed the case. So here the picture would be that we have two lines that intersect in a point. So the intersection is not a divisor. It's of codimension 2, not codimension 1 on a plane. However, this blow-up operation, okay, in this case, the blow-up looks like this. We blow up this point, it becomes a line. And if we look at the preimages of this divisor in this blow-up, then we get this divisor plus this divisor. And the inverse image of this divisor is this divisor plus this divisor. So here, this part is the minimum. Okay. Right. So one can form a real vector space of adelic divisors by passing to blowups. So then it only depends on the function field of the variety, and then it is a real vector space that has lattice operations. And one can also define maximum dually, or in this case, one just takes the sum of all components. Okay, and then if we have maximum, we have also effective cone, which is the cone of elements such that maximum with 0 doesn't change them. So this is only taking the positive components in the decomposition of the divisor. Okay, so the divisors in arithmetic geometry, they are objects that parameterize heights. So the definition of Weyl projective height may seem a bit arbitrary, but this formula is more canonical, at least for arithmetic geometers. And so the point is that whenever you have an adelic divisor, let's say that it's effective, and we have a point in the generic fiber of our arithmetic variety, then we can define its height. So the intuition here is that our arithmetic variety looks like this. It lives over spec Z. So this is curly X. We have here the generic fiber. This lives over the generic point of spec Z, so spec Q. It's a closed point here, small x. And besides that, we have this divisor D with some extra analytic structure. So this X
This is an invention, though. I mean, I think also special applause for David for his excellent.
So ask Tom whether he can hear. Oh, yes.
I'm I'm testing. Test. Can you hear that?
Yeah, it's fine. Thank you. Yes, it's good.
Oh yeah, maybe one needs to share sound as well.
Is the sound on? Yeah, the mic is picking something.
Yes, it's okay.
The mic is picking stuff.
Yes.
It's fine. So Tom hears.
Okay.
So I don't think you can go too far, but
Yeah. Okay.
it's not ideal.
Okay. I can speak. But can we?
Maybe close the chat. I was
Or you get some
look at the chat.
I forget that this is the one.
Oh, but I can.
Oh, this is not working anymore?
Oh, but then you just speak on the.
Yes. And now? Okay.
Okay.
Sorry.
Okay.
So
Okay.
you have to do it by hand? No, sorry. I just need to activate the window.
Okay. So to summarize it up, we defined this lattice structure on adelic divisors. So we can also apply tropical polynomials now to principal divisors. So these are the ones in the green example. And then with adelic divisors, we have associated a function on the space of on the generic fiber, on Q bar points of the generic fiber. And then this function, if our adelic divisor is some tropical polynomial applied to some tuple of rational functions, is in fact recovers back the tropical predicate that was introduced at the beginning on Q bar of 1. Okay, so now what's the correspondence? Why? So in fact, it's a part of a deeper story, namely call a functional from adelic divisors of the function field to reals, so linear map, a normalized GVF functional if it satisfies the following 3 conditions. So first of all, it sends principal divisors to 0. So this corresponds to the product formula. Second of all, it sends effective, so these positive arithmetic divisors to non-negative numbers. So it respects the lattice structure. And the last part is a normalization part. So height of 2 is supposed to be log 2, and that's why this adelic divisor is sent to log 2. So then the GVF structures on the function field of the variety extending the standard one corresponds to GVF functionals on the space of adelic divisors. So, well, this is maybe not that unexpected in a sense that GVF structure, whenever we have a tropical polynomial and a tuple of functions, one gets a number. And in the geometric language, one can think of these tropical polynomials together with tuples of rational functions as some geometric objects, these adelic divisors, and then a GVF structure is a functional on the space of adelic divisors that satisfies the same properties. So here the correspondence is given by the following equation. So, for example, if we have a GVF functional as above, then we can define predicates RT of A just by applying this functional on the adelic divisors given by this tropical applied on the corresponding tuple of rational functions. Okay, and the last part of oracle of geometry that we need is arithmetic intersection product. So the point is that if we have D+1, or here, if we have a K+1 dimensional subvariety of our arithmetic variety and a K+1 adelic divisors on it, then we can intersect them. So this is the generalization of this intersection that was showed on the board there. And we get numbers that we will see the definition later. And height is a part of this family of numbers. So yeah, this is what this picture was presenting. And this arithmetic degree is multilinear and is defined inductively by the following formula. So to look at this inductive definition, we take the last arithmetic adelic divisor and we intersect it with the subvariety. So then, at least in the transversal case, we can decompose it as a sum of some one-dimensional less varieties together with some weights. And the formula looks like this. We have the parts corresponding to smaller dimensional varieties, and then we have the part corresponding to complex analysis, where we take the green function of the last divisor and we intersect it in an analytic way, looking at Chern classes of the line bundle corresponding to the divisors d0 and dk-1 with a metric corresponding to the green function. Or these Chern classes, one can also see them as currents associated to the green functions. So yeah, I don't think I have time to go into details here. But yeah, this is an analytic part of the formula. And then if we have d plus one dimensional arithmetic variety, the intersection, we write it without the degree. Okay. So let's now go to the proof of the main result. How does it use oracle of geometry and this intersection product? So from the point of view of these GBF functionals,